Good morning, everyone. Thank you for making it, those of you who could. So my name is Dr. James Cole. I've recently finished my PhD, where for the last 3.5 years I've been working on extracting water ice from icy simulants. Today, and specifically, I'm going to be talking about the last section of my work, where I worked on extracting ice from different forms of icy simulants, so where I made the ice in different ways. So, as you may have heard through the last few days and through the last few years, we're pretty sure now that there's water at the poles of the moon, and water is going to be one of the most useful space resources for our use in space exploration, particularly in its use as a fuel, a propellant, particularly in its use for a sustainable cislunar economy, where we can work on refueling satellites in cislunar space and possibly even launching rockets from the lunar surface. The only problem with this is that at the poles, the lunar water ice exists in incredibly difficult conditions. It exists at temperatures as low as 40 Kelvin, it exists in the vacuum of the lunar environment, and there is no sunlight, which means that any probe or any rover you send down there is not going to survive for very long. And this means we need to find techniques of removing this water ice as quickly as possible. Many different techniques have been looked into extracting this water ice, but they all mainly revolve around thermal mining, so essentially just heating up the icy regolith and collecting the water ice on the rover and then getting out. So if you're looking at the traditional technique, that would mainly be a heating element or on a drill cuttings, and maybe even something like solar sintering, where you concentrate some sunlight from higher up into the PSR. When I started my project, I inherited the sort of heritage microwave system that Sungwoo mentioned earlier. And I thought, well, if we can heat up simulants efficiently to thousands of degrees for sintering, why not look at heating up very cold things to see if we can extract the water ice efficiently? So this is the heritage microwave system that we've got. So it's been used for a number of years now and designed primarily for sintering experiments, so going to very high temperatures. It can produce 0 to 200 to 1,000 watt microwaves at 2.45 gigahertz. So it's a stationary frequency. We can't adjust the frequency. It uses an adjustable tuner, so we can set up a standing wave regime where hotspots occur, and this is where the maximum electric field occurs. So it's where you want to place your sample. We at the back end, we've connected it to a vacuum system, which is attached to a mass spectrometer, so we can analyze any of the gases that are released, and we can get down to pressures of roughly 10 to the -5 millibar. And so, yeah, as I said, when I inherited this piece of equipment, it was mainly being used for sintering experiments. So I had to work for a while on adjusting it to water extraction, finding where was the best way of doing that. And actually, I performed a few experiments where I adjusted the water content and the simulant type, so Mario Highland, for different samples, and looked at the water, the extraction occurring. And that's in the first paper mentioned there. One thing I did notice was that, quite obviously, I suppose, if you adjust the heating time, you can change the amount of water coming out. What I did find was that the rate of water would change over time. The rate of water extraction would change over time. And at the time, I was just simply measuring the mass before and after taking it in and out of the microwave chamber, where it wasn't the most efficient way of doing so. And we couldn't guarantee that the samples between each type were consistent, or all the properties were consistent. So I looked into building a mass instrument that could measure the real-time mass loss from samples, and meaning that each sample I knew was fairly consistent, and I could change the heating time and look at how the mass loss changed over time. So I did so by using a load cell, and I isolated it from the microwave system using a very small gap, and then using microwave transparent materials from there. So it can measure masses between 100 to 200 grams to a resolution of about plus or minus 0.1 grams. All the gory details of the calibrations and the preliminary experiments can be found in the paper mentioned here, where I essentially made sure that it could work at the different conditions I required for my experiments. So for this work, I wanted to look at the different forms of ice. So I looked into, and we don't really know what the true composition of the ice at the poles is. So I looked into building sort of the two, I would say, most straightforward forms of icy regolith you can make. So the first one would be diffuse ice, which is where you essentially add liquid water to room temperature simulant. You just mix it as well as you can, and then you cool it down to 100 Kelvin with our setup. And the whole idea was this is sort of the permafrost technique, which had quite a lot of heritage. It's got quite a few papers and people looking into using it this way. And then I also created cryogenic ices and then crushed them using a hammer and then sieved them through cryogenic sieves to get to a particular size range. And I made two different ice grain sizes for that. And again, then you add it to already cold simulants so that the ice grains don't remelt. And then again, try and mix them as well as you can. Apart from that, as that was the only variable I wanted to look into, everything else was kept consistent. So the mass of the sample was about 40 grams. The simulant was kept as LHS1, which is a Highland simulant, again, most likely what the poles represent. And the water content was kept at 5 weight percent, targeting roughly the L-cross results. So as I mentioned, the first paper I had produced looked into the adjustment of water content and the mineralogy of the simulant. So I wanted to look at, firstly, how the form of ice affects the water extraction, so diffuse ice versus granular ice. And then also, from the first paper, I found that the surface area of the ice had an impact on the water extraction. So I wanted to look into surface area, and that's why I've got the two different grain sizes. With the diffuse ice, it's very difficult to quantify the surface area, whereas with the individual grains of ice, we can make an assumption of what the true surface area is. Apart from that, the experiments were kept consistent. So I heated them in the microwave heating unit for 60 minutes using 250-watt microwaves. And then I used the mass instrument to measure the mass loss over time. So first thing to note, if you look at the table on the top right, and these mass measurements are using the old system where I just measured the mass before and after. The first thing to mention, if you look at the extraction ratio, is that the extraction is quite high for all of them. And there's actually not a great deal of difference between all of them. So this is actually this is a good thing for microwave heating in terms of its water extraction potential, in that it doesn't really matter what type of water ice we end up finding. It should be okay at still extracting them fairly consistently. And then if we look on the bottom right, we can see the graph of mass loss over time using the mass instrument. And luckily, the graph actually shows. I was very worried it was going to be a black box. But so for the first sort of 600 seconds, there was no microwave heating on. This was just to allow the mass instrument to get a consistent result and also to check that the mass wasn't being lost too quickly in the vacuum of the system. And then there was about an hour of heating where for the diffuse ice and the smaller grained granular ice, the trends are fairly consistent, which to me suggests that at the smaller grain sizes, it's almost acting like a well-diffused ice, very well mixed ice. And then for the larger grain sizes, we see two significant drops of extraction, which again suggests that it's doing something differently to what the other types of ice were doing. Now, as I mentioned already, about 80% of the water was extracted for all samples, which gives you about an energy efficiency of 8 milligrams per watt hour, which compared to other solar sintering experiments is kind of comparable. Now, obviously, solar sintering is using free energy. It's not using any energy sources, but there are advantages to using microwave heating. The scalability should be quite good, and the reliability of using it should be quite good as well. So for what I was looking into, I tried to come up with some preliminary thoughts on why these things were occurring. So for the forms of ice, the water extraction from the diffuse ice is a fairly constant rate. That's probably just due to the fact that the water is diffuse across the sample. So as the sample heats up, the water is released at a fairly constant rate. And this is probably also the reason why it happens with the smaller grain sizes. As I mentioned, the smaller grains probably are acting like diffuse ice because they're diffused through the system. For the larger ice, you're seeing something quite different in the way the extraction drops. And that's probably just due to the fact that we were keeping them out of water consistent. So you've got less of them, but larger chunks. And so it comes out in discrete forms as they heat up. For the surface area, actually, we found something quite what I wasn't expecting. So for the smaller grains of ice, you'd expect, higher surface area or more in contact with the simulant, and therefore you'd expect a higher water loss going on. But actually what we found was the other way around. The larger grains were producing a higher water loss. So the reason I think this is happening is that as the grains are heated, the larger grains are producing more vapor within a grain, and that leads to a higher pressure, and that leads to a higher water mobility through the sample, so that you're able to produce more water. It's also why it comes out in large chunks. You first get rid of the sort of surface ice, and then these larger ones come through, making use of the void spaces already left behind from the previous ice grains. So it seems to suggest that the larger ice grains might be more susceptible to microwave heating, but obviously this needs to be looked into further to analyze what's really going on. So in summary, and sort of a summary of also what I found out throughout my PhD, is that microwave heating is an effective technique for water extraction, even though microwave heating shouldn't be as good at lower temperatures. It seems it can produce a lot of water. And I think it could be further improved with a dedicated system for this. At the moment we are using a sintering system. I believe a more open source cavity would be better rather than a standing wave configuration. We found that different ices have different extraction profiles, maybe not entirely surprising. And we need to do some further work on analyzing why this is occurring. But the good thing is that the extraction is high for all of them, really. And I think one of the things I really wanted to look into, but we never got a chance to, was the different frequencies. So at the moment, we're just using 2.45 gigahertz, which is just what your microwave at home is producing. But water ice isn't actually very susceptible to microwaves at that frequency. So if we could look into using different frequencies to see how that impacts the extraction, that would be really good. And then again, other things like varying the input power to see how that's. I think we could even go lower than, because at the moment we're using 250 watts. I think we could go much lower and just heat it for longer. And then maybe the addition of susceptors further down the line. But yeah, that's all I've got to speak to you. All right. Cool.
Thank you very much, James. I'm sure there are some questions from the audience. If there are no immediate questions, I have one. It looks from your setup like you use a stationary positioning for the sample in the cavity.
Yeah.
And you use standing wave patterns. Do you have to worry about hot spots and cold spots in the standing wave pattern?
So we calibrate the microwave beforehand, where we can analyze where the hotspot's going to occur, and then it occurs at a fairly consistent placement. So we place the sample on ceramic plinths that raise it to the correct height. But yes, if you were going in between those, you'd get much worse heating profiles. I think we've got one more question.
Yeah. Hi, since we're running other questions, one more is this one related to system efficiency. What with abundance of water ice being potentially 2%, a lot of energy can go into the heating of the regolith itself. Does microwave heating enable the preferential heating of the ice itself, so you could potentially have greater system efficiency, heating preferentially the ice instead of the regolith as well, quicker, lower energy extraction?
I think that's kind of coming down to the frequency point I made right at the end there, where I think the frequency at the moment is set up for better heating of the simulant rather than the ice. However, the problem with that is that where ice is most susceptible to microwave heating, you're at a frequency where your penetration depth is really small. So there needs to be a systems architecture play off there between how far into the sample you want to heat, especially if we are using an open source microwave straight onto the surface. If the ice is tens of centimeters down, there needs to be that play off between what we're doing.